It's a great opportunity to be here with you in Merida, talking about a topic that I find really fascinating to think about, and I think it has great importance in the 21st century. So what I'd like to do is to spend the next 20-25 minutes going over a number of high-level concepts and introducing people who have different levels of expertise in different areas to some of the differences in areas, and perhaps introduce some vocabulary if need be. But I think that it'll be, I'm sort of the warm-up act for Chetan and Marcelo, in a sense. So they'll go into more detail about their areas. I will talk a little bit about drugs because Pedro's not here, and we'll talk a bit about that, and I'll spend some time on international aspects and epidemiology, things that interest me programmatically as well. So I think that it's fair to say everybody here is probably familiar with the latest data on malaria and the tremendous burden that it imposes globally. There are still 207 million clinical cases, 627 deaths annually in 2012, an ongoing transmission, and 45% of the population, of the world's population, is at risk due to 5 different Plasmodium species. But as shocking in some sense as those numbers are, they represent a vast improvement over where we were a number of years ago. And we have undertaken a very, very aggressive, as a global community, we have undertaken a very aggressive strategy to eliminate malaria in the past decade, which basically pursued aggressive control in high burden regions, progressive elimination from endemic area regions, so-called shrinking the map, and trying to expand the R&D pipeline to develop new tools and techniques that would enable us to better control malaria. Now, all 3 of these are absolutely critical, and they need to be pursued simultaneously. But we've been doing that, and the evidence that we're having an impact is shown on this slide, where you can, we've had a 26% reduction in malaria mortality in the decade from 2000 to 2010, including a 33% reduction in the most highly afflicted area in Africa. 50 countries are on track to reduce malaria incidence by 75% by 2015. And what you can see in this map here is that this area here, you can see these large areas that are green are areas that where malaria are malaria-free. These areas that are blue are areas that are now eliminating malaria, and the areas that are red are areas that are controlling malaria much more effectively. So we have made tremendous progress in the past decade, so much so that we can actually anticipate and the possibility of malaria eradication, or the so-called future perfect. This was actually raised We're going too far. Can we go back one slide? Okay, the possibility of malaria eradication had actually been raised back in the late 50s and was pursued rather aggressively, and then it proved to be extremely difficult at that time and was gradually abandoned. But in 2007, at the Gates Malaria Forum, the possibility of eradicating malaria again was raised. But I think the crucial difference here was that, and this came up in some of the discussions that went on at an initiative called Malaria, was that research had to be an integral part of any sort of future eradication effort. And even in this early setting here, where Bill and Melinda Gates were talking about malaria eradication, the important issue here that was raised was developing the scientific breakthroughs that would be needed to end this disease. And that's what we're going to talk quite a bit about over the next several days. Okay, so one of the points that as I was thinking about this that was rather interesting is that this is not without precedent. There has been an ongoing discussion about the appropriate role of science in a variety of different activities. And there's this tension that sometimes exists in the community between the quest for trying to improve our fundamental understanding and people who are really interested in saying, no, 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 we need to use the science to achieve some objective. And this was actually brought out very nicely in a book by Donald Stokes in 1997, where he talked about science as being grouped into different quadrants. So depending on whether you were pursuing fundamental understanding or considering use primarily. So for those of you who are interested, fundamental understanding as envisioned by Niels Bohr, the physicist, was basically, I want to understand how how an atom works, and I don't really care how it's used. He didn't necessarily say it that way, but that was sort of what motivated. His motivation was really to understand the atom. In contrast, you had people like Thomas Edison who basically said, you know, I just care that I have a better light bulb. I don't really care why I have a better light bulb, but I want a better light bulb. But then the interesting category here is those people who try to pursue both. And the example of that is mentioned in this book is Pasteur. And Pasteur's research was largely motivated by his desire to have a practical effect, but he realized that in order to do that, he was going to have to go back and understand some fundamental processes, whether that was understanding how anthrax caused disease and trying to develop a vaccine for anthrax, or whether it was understanding fermentation better so he could produce a better beer, which was actually an important product for Alsace, the part of France that he was living in. So he had yes, he was very practical, but he really believed in going back to fundamental roots of science and understanding what that was. And I would argue that malaria eradication is very similar in that sense. We have a very practical long-term objective here. We want to eradicate a disease. We know it's been done before for other diseases. We believe that it can be done for malaria. What we don't have is all the tools, but we know, or we believe, that science, when applied appropriately, can actually provide insights that will enable us to develop those tools. So how do we get from malaria elimination to eradication? Well, first of all, we need to acknowledge up front that eradication is a long-term futuristic goal. And it will have to be built on new epidemiologic scenarios because it is not a static target that we are dealing with. And it will require improved use of current tools, adaptation of those tools to new epidemiologic scenarios. We will need to discover, develop, and evaluate new tools, and we will need to effectively integrate multiple different interventions across different programs and across different settings if we are going to achieve this objective. And so what I'm going to do is to go through some aspects of these different tools and the processes by which we are trying to achieve some of these objectives. Around the same time that the Gates Malaria Forum came out with the call for malaria eradication at NIAID, we were actually revamping our strategic plan and research agenda, and in fact we came up with these two documents which are available on the web. And actually what was interesting is that they actually anticipated a lot of the issues that came up as the efforts to pursue malaria eradication became formulated. One of the key issues that I've already alluded to, but which is also mentioned in this report, is the fact that there are a variety of different interventional approaches that one could take to achieve malaria eradication, whether we're talking about vaccines or therapeutics or vector management. And some of these are sort of more traditional elements, over in here, for example, but some of them require new understanding and a better approach to accelerate their development. For example, gametocytocidal drugs or transgenic mosquitoes. And some of these are things that Chetan and Marcelo, I'm sure, will be going into, unless I've completely missed the boat here. But okay, so given that we have multiple interventions and that they're being applied effectively, the thing that we are seeing, which you saw on that map, is that there are some major changes occurring in the epidemiology of malaria. That's very interesting, very encouraging, but what does it mean for the future directions of our research? And here, I've just highlighted some of the issues that will be coming up over the next several years as we continue to make progress in these areas. But if one thinks about the rapidly changing epidemiology with decreased incidence and transmission, then we have to start thinking about things like the possibility that there will be changes in the target populations for the interventions. How are we going to diagnose the disease? Are there optimal mixes of interventions that we would want to use in certain settings and not in other settings? As the incidence of disease goes down, trial size can go way up. And for transmission blocking vaccines, we may need to rethink the conventional trial designs and use cluster designed trials as an example more efficiently and more effectively. Or we have to develop alternative endpoints that would allow us to think differently about this. There's been an increased interest in non-falciparum malaria outside of Africa and an increased interest in non-Gambiense anopheline vectors. As I'll show you in a little bit, there's been, not surprisingly, increased drug resistance and tolerance. So how do we address this? We're going to have to think about new drug combinations, new drugs, novel diagnostics for drug resistance, and how they fit into some of these control strategies. Emerging insecticide resistance and altered vector behavior may also represent opportunities or pose new challenges for thinking about how we are going to move forward with our control programs and our development of interventions. And then the potential licensure of a first-generation malaria vaccine has a whole lot of implications for how the vaccines would be integrated into malaria control, elimination, eradication programs, and what are the expectations, the so-called current status for therapy or for prevention if a new vaccine is introduced. And then how will that affect future development of new vaccines? So thinking about these in that context of the strategic plan and the research agenda that we had put together, Dr. Fauci and I, as we were thinking about these, came up with this, wrote this article in which we were trying to emphasize that just as the epidemiology was changing, we would have to have a responsive biomedical research agenda that would also evolve in response to the changing needs. And we identified 5 challenges, which are listed here, including translating genomics and a variety of other new tools into new interventions, improving our ability to diagnose malaria, blocking transmission, and expanding the research base for Plasmodium vivax and other human non-falciparum malarias. These 2 are of particular interest for eradication. And then ensuring that this was a sustainable enterprise that could endure over a long period of time that would be required for research and development to eradicate malaria. We based our conclusions and our recommendations coming out of that, our perspective, on the biology of the parasite. This shows the life cycle, and obviously there are a number of points of interventions, whether it's in the mosquito, in the pre-erythrocytic stage, in the asexual blood stage, or in the sexual stage. But also of interest here were these 2 transmission bottlenecks that existed occurring when parasites are transmitted from humans to mosquitoes or from mosquitoes back to humans. And we'll talk a little bit more about that. The other thing that I think is important to recommend or to consider when discussing eradication is that a lot of the efforts to date have been focused on falciparum, but when you think about vivax, there are important differences in the life cycle. that impact our ability to control, eliminate, and potentially eradicate vivax. And I've listed some of them here because they have implications for the types of interventions that we would want to think about developing. So for example, falciparum can complete its life cycle in the mosquito, its maturation period, at 16 degrees, but Vivax actually can survive at lower temperatures. Vivax has a dormant liver stage, falciparum does not, and gametocytes in Vivax appear concurrently with asexual blood stages, often when individuals are asymptomatic, whereas with falciparum they occur after asexual blood stage infection is established. So these biological differences inform the types of interventions that we would think about developing. In terms of diagnostics, microscopy really remains widely used, but RDTs have been used increasingly as they become less expensive. And the great advantage is that they improve the diagnosis, make it more accurate, they promote appropriate treatments, and they reduce the expenses of malaria control as they allow people to be more targeted. But RDTs aren't necessarily going to function the same in high incidence settings as they do in low incidence settings, and we may have to rethink how we're using those in the future. So basically that's this point here about improving them and refining them for low incidence settings. We'd like to move to non-invasive sampling and detection of G6PD deficiency in patients with Vivax infection, so we can actually treat them or treat large portions of the population with drugs that actually elicit adverse events in some individuals with this metabolic deficiency. Some of the clear and present dangers to our success to date include artemisinin resistance in Southeast Asia and insecticide resistance in Africa. So efforts to contain artemisinin resistance are ongoing. The WHO came out with this global plan for artemisinin resistance containment. This is what the situation was in 2012, and all these red dots here indicate the areas of confirmed or suspected artemisinin resistance. The situation has continued to progress, so much so that the WHO then came out with an emergency response to artemisinin resistance in the greater Mekong region. So this is obviously a major concern. What that really means for us is that we have to think about different types of drugs as well. So here are some unmet needs for malaria therapeutics. Some of these are actually discussed in the Malaria book that you all received on your chairs. But some of the unmet needs here are we'd like to see a simple short course to improve compliance. We'd like to have drugs that overcome resistance. We'd like to be able to prevent and treat liver stage infection, including preventing relapse. And we'd like drugs that block transmission in order to move us closer towards eradication. The good news is that just in the last year, 1 to 2 years, we've seen a dramatic increase in the number of compounds that have been identified that actually fit different parts of the research agenda. So NITD 609 may actually offer a single dose cure. This is currently in phase 2 clinical trials. DSM 265 may be useful for prophylaxis and has liver stage activity. It's in a phase 1 clinical trial with MMV at the moment. And ELQ 300 is actually active in liver, blood stages, and in blocking transmission, and is being pursued preclinically. So the spectrum or the timeline by which these appeared actually happens to perhaps reflect our thinking as we've gone from simple trying to improve the dosing to actually trying to improve activity against stages that are of particular interest for eradication. One of the ways that this has been made possible is the fact that at NIAID, we don't just support researchers to do the actual investigation. That's really important. But it's also important to be able to support this product development pipeline, which goes all the way from discovery through to licensure. These are the grant mechanisms that most NIH grantees are familiar with, and people such as yourselves could actually apply for some of these. But in addition to that, we have a variety of contract resources that people can access through the NIH that will provide data back, for example, on preclinical toxicology or on formulation. Sometimes they will actually synthesize product for clinical trials, and in some cases we actually carry out the clinical trials that are meant to accelerate the evaluation of these products, both in the US and overseas, with the idea that they would be moving into licensure and implementation. As I said, insecticide resistance has also been a major issue. At least resistance to at least one insecticide used for malaria control has been detected in 64 countries. But as Marcelo will talk about, there are a variety of novel approaches that are being pursued, and I'll let him go into the details of this. But there are lots of different things that I'm sure he'll be very excited to share with you. Let me talk a little bit about vaccines, and I don't want to steal Chetan's thunder, but just to emphasize that some of the biological and epidemiologic characteristics that are important are for an eradication agenda are looking at vaccines for non-falciparum malaria, low incidence settings, and the impact on interrupting transmission. This is different from what we have been developing under usual control scenarios where we're trying to reduce the burden of disease. And this was actually highlighted in this article by Brian Greenwood and Jeff Target, where they talked about the target product profiles and contrasted them for a vaccine for malaria control and a vaccine for malaria elimination. And here you can see the target population is high-risk groups. Here we're talking about the total population. They have differences in efficacy, differences with respect to the duration of action, differences in terms of their biological targets, and then their delivery program as well. So it's very important as we start thinking about the types of products we want, we have to think about how they will ultimately be used, and that in turn informs the type of research that we would like to be pursuing. Let me turn to the genomic base. We are very fortunate, although we have a very complex life cycle for malaria parasites. We actually have genomes for all three major players, the human host, mosquito vectors, and both falciparum and vivax, and a number of rodent models as well. And we can now try to tap that reservoir of data in order to inform our efforts to develop new interventions. We are also standing on the cusp of a revolution in the way we approach a lot of biological data, because we can handle much larger data sets now and take a more systemic approach, a systems biology approach. We recently supported this new program, the Malaria Host Pathogen Interaction Center, which the reason I show you this slide is just to demonstrate the diversity of approaches that these investigators are able to take using new technologies that can be brought to bear on some very old but still unresolved questions. Finally, let me talk a little bit about our International Centers of Excellence in Malaria Research. This is a program that we launched in 2010. The idea here was to get a better handle on the changing epidemiology of malaria in a variety of parts of the world. And what you can see here is that we were fortunate in that we were able to make awards in each of these areas that are circled. So we are able to span a variety of different epidemiologies with the research awards. The real challenge, however, becomes, it's great, you've got all these centers that are generating tremendous amounts of data, but how do you get information out of it? So we have 20 isomers, or 10 isomers, working in 20 countries at more than 50 field sites. And over the next, the period from 2010 to 2017, they're collecting data on a whole variety of different levels, individual, regional, and global. The question is, data, how would you handle that? So you can take the metadata, and we have instrumentation and databases, but how do we ensure comparability across the different sites? One of the ways that we've decided to approach this is that for a variety of assay data and quality control data and lab management systems, we've put in place standard operating procedures and reagents so that we can actually crosswalk the data across different centers and ensure comparability that way. And that we believe that there is great value to being able to do that over time. So that brings me back to an important relationship that I want to focus on for a minute, and that is, what is the actual relationship between the laboratory and the field as we think about eradication? In the past, much of the efforts have been focused on product development being driven from the laboratory to the field. And what has often, unfortunately, happened is that we get out to the field and we discover that the product that we have doesn't really match the reality of what's going on in the field any longer. But with the data that we're now collecting and the tools that we have available as we start thinking about moving forward, we are in a much better position. And we can actually start thinking about ways to take advantage of this and actually use the data we're collecting from the field to inform product design that goes back into the laboratory so that as we proceed further forward with product development, it is better suited to what's going on in the field. And we can modify it as time goes on because we'll be collecting data and we'll be in a better position to do that. So let me just give you one example, which I think is really quite interesting, and you'll probably hear more about it tomorrow or the day after. This is actually from Karen Day's work, showing that there is a correlation between transmission intensity and the parasite population diversity. So high transmission intensity, high population diversity in the parasite population. The question that we are faced with in an elimination or as we approach eradication scenario is, if we reduce the incidence or transmission intensity, are we going to see a reduction in the diversity of the parasite population, or are we going to just see a smaller group of equally divergent parasites in the population? And the answer, at least coming out of studies in Senegal that were carried out by a group of isomer investigators, is that in fact, as control programs and elimination programs were rolled out, what you can see here in the graph down at the bottom here is that the level of complexity is starting to go down as the control program is being enacted. So this has a couple of implications. One is that we can actually use genetic surveillance to evaluate the effectiveness of some of these control strategies. On the one hand, that's actually a very interesting observation. But perhaps another equally interesting, but perhaps a little bit more speculative aspect of that is that if the genomic complexity is going down, we may be able to selectively target some of the aspects of those parasites that are persisting so that we can actually have a more rational approach to eliminate or eradicate those parasites in the future. So the final challenge as we move forward in the role of the evolving biomedical research agenda is to ensure the vigor and sustainability of the substantial biomedical research efforts that are going to be required. I just want to make the point that this is an aspect of collaborative global health research, and it's going to involve a whole lot of people, not just a group of scientists, but a whole lot of other groups that will also be influenced and be influencing what goes on here. And we need to engage them and have discussions with them as well. And critical to this effort is the fact that broad-based community engagement take place. You've received a copy of this journal, this special supplement to PLOS Medicine that came out. This was published after a 2-year consultation process. This was published in January 2011. And the important issue here is that it identifies actionable research based on global community input that could move us towards elimination and ultimately towards eradication. So I hope you'll take a look at that, review it, use it as a reference, and I hope it'll stimulate your thinking about new ideas and new approaches. And so let me just summarize by saying that we have actually been remarkably successful in our attempts to control and eliminate malaria, but the success that we've had is still at risk of, substantial risk of reversal. The evolving nature of malaria epidemiology in response to these ongoing control and elimination efforts demands an adaptive, flexible, multidisciplinary approach to sustain our momentum, and that progress towards eradication will require continuous improvement, innovation, implementation, and adaptation of interventions against malaria. So we need to engage others in an ongoing dialogue across the full spectrum of R&D and across the full spectrum of public health efforts that will be critical to this effort. And I'm happy to take any questions if anybody has any. But thank you for listening.